can hear me. Thank you for being here. It's the last session. We made it to the end of the week, and thanks to the organizers for a successful conference. As mentioned, my name is Ash. I'm a PhD candidate at Toronto Metropolitan University in the Department of Mathematics, working with Dr. Paul Perlat. And today I want to present a work that myself and our colleagues here, who some of you guys will recognize in the room, on an unsupervised framework for evaluating node structural embeddings of graphs. This work was done in collaboration with our partners at Warsaw School of Economics and also our industry partners, Patagonia Technologies. By the way, I'm going to use my own laser pointer since the other one has the button of death, so I'll just use this one for now. Hopefully you guys can see the red dots. So here's an outline of what I'll be talking about today. I'm going to start by telling you a little bit about embeddings. We heard about embeddings throughout this week, so I'm not going to spend too much time on that. Then I'll talk about our framework, some of the questions and problems that we were thinking about when we developed this framework and some of the challenges we faced. Then I'll walk you through the algorithm itself, walk through the framework and some of its properties, but I'll spend most of the presentation talking about various different case studies where we use both synthetic and also real network to analyze these systems just to showcase how one could use this framework in a practical setting. And of course, at the end, I'll conclude and I'll talk about some potential questions that we can work on next. So embeddings, I'm sure some of you guys know about embeddings already, but we can think of embeddings as a collection of algorithms that perform two very important tasks. One is data compression, the other one is data organization. So data compression is easy to see. We take a large, complex, n-dimensional graph, and we map it into a much smaller k-dimensional continuous vector space, which we call the embedding space. So here, n is much larger than k. And this is very useful for practical purposes. As we heard yesterday with Twitter network or Bitcoin network, these networks can be very large, so hundreds of thousands, millions, or billions of nodes or edges. So dealing with systems of that large is very difficult. So working with a much smaller regular data set with, for example, 32 dimensions or 128 dimensions is much better. As Paul mentioned earlier this week, we have hundreds of different embedding techniques. Each one of them is designed to learn something different about a graph. And the information that those techniques learn from the graph allows us to organize the data in the embedded space. So this is very useful for downstream tasks such as clustering, classification, node, edge prediction, node coloring, and things of that nature. So these hundreds of different embedding techniques can be classified in many different ways. For example, if they're based on random walks or deep learning techniques, the way we classify embedding techniques is into two domains. One is called classical embeddings, the other one is called structural embeddings. Classical embeddings such as node-to-vec or deep walk are designed to capture proximity within the graph, so how close are nodes to each other. They're very useful for recommendation systems, for example, on Facebook or social media. So a friend of a friend who's closer to you is more likely to be your friend as compared to someone who lives across the world. On the other hand, structural embedding techniques are designed to capture the representation of the local structure around nodes. And this tells us something about the role that node plays within its local community. So systems such as struct-to-vec or roll-to-vec are designed to capture exactly that. And applications of this, as we saw yesterday, could be bot detection on Twitter, for example. So two different nodes that are not really close to each other on a network could play very similar roles to one another. So you have a node that's a bot advertising to high net worth individual in the United States, a similar node doing the exact same thing in, for example, China. So they're not really close to each other on whatever network they're on, but they play very similar roles. So this is kind of a cartoon representation trying to depict that. So the framework that we've developed is designed to work on this second type of embedding techniques. So one of the natural questions that usually comes up when we're dealing with machine learning techniques is, what are these embeddings or machine learning techniques actually learning? This is obviously a very hot topic today with large language models or computer vision techniques, but this also applies to graph embeddings or node embeddings. So what features about a graph are these techniques learning? Now, for simple algorithms, it's easy for us to look inside and look at the technique and see what's actually happening. But for techniques that rely on deep learning or a bit more complicated, it's not easy. And a lot of times you don't have access to the raw code to look at the algorithm itself. The second question that comes up is, if we can understand what features are being learned by these techniques, how well are these features being learned? So for example, if I have two embedding techniques, both of them learning PageRank, which one of them is learning it better? Because this allows me to pick the right algorithm for a particular task. But I think the more important question is, or potential use cases, if I can understand what features are being learned by different techniques, I can combine the result of different embeddings, so I get a much broader representation of the graph as compared to picking techniques, which all learn the exact same thing. Now, we're very lucky because there's a collection of papers by these lovely folks here who you'll recognize that answer these two questions, but for the classical embedding techniques. Actually, there's a collection of papers that you can take a look at. But this technique wasn't extended to structural embedding. So this is kind of the motivation for us to take similar ideas and similar questions and try to build a framework to answer this question for structural technique. Now, before I jump into the algorithm itself or walk you through the framework, the key point here is this unsupervised word. Now, why do we care about unsupervised? Is because a lot of the networks out there, a lot of the data out there is not labeled. So we want our framework to be applied to any network possible. And the second reason is if we try to answer these two questions for labeled data sets, we don't know how much of the answer we're getting depends on the label. So in other words, if I relabel my data, for example, instead of bot versus not bot, go to hostile actors on Twitter, do I get similar information or not? So let's jump into the algorithm itself. So this is a kind of cartoon representation of the framework. There's a more mathematical version of this in the paper that we're working on for people that are more mathematician. But let's start all the way on top here. So we have a graph that we would like to embed. Now let's imagine we have a closed box embedding technique that we have no idea what it does. But it doesn't matter really to us. We can just plug it into the embedding technique and it embeds all the nodes into some k-dimensional embedded space. Now here the colors are really just from a comparison perspective, so they don't mean anything. So these k-dimensional embedding space works great, but we have no idea what these dimensions actually mean. They're kind of cryptic. So to be able to explain what these dimensions means, we create a parallel world or universe where we design a feature space where the dimensions of that feature space are metrics that we can actually understand. So we can calculate these metrics. For example, I can map this graph into this feature space and then set the first dimension to be the page rank for every node, the second to be degree centrality, and so on and so forth. So I can map my graph into a m-dimensional feature space where again, dimensions are what I set for myself. So from a practitioner's point of view, that's something you set. Now, one thing I want to point out, yeah, of course.
You calculate the page rank for every node. So you calculate the average or just one graph map into one box or you calculate like if you have n nodes, you calculate n page ranks.
That's correct, yeah. We calculate.
How is n related to the dimension of that?
Also, this is m different type of metrics. So here, for example, if I have only page rank, this m would be 1. So I have a one-dimensional feature space where I calculate page rank for every node. If I have a two-dimensional, correct, yeah. So the dimensions here, the m dimension and k dimensions don't have to be the same. So they could be, I could have a 500-dimensional embedding space and a one-dimensional feature space. And the idea is that the dimensions or the kind of metrics features I choose in the space here allows me to explain my embedding according to, again, what metrics I'm interested in. So now I have two spaces, one which is an embedding space, the other one is a feature space. So I understand what the feature space is composed of, but I have no idea what the embedding space is composed of. So we need to create a bridge between these two. So the first thing I do is I create a clustering of all the different nodes. So I create S number of clusters. And what I can do is I can calculate the distance between nodes of these clusters. So I can create a between cluster, so for example, A and B or A and C using this metric here, the Euclidean distance here. So this is pretty straightforward. This allows us to get a vector of distances between different nodes. Now what I can do is I can go into embedding space and do the exact same calculation there. So I can calculate the distance between A and C, A and B, so on and so forth, and calculate that. So I'm not going to do a clustering in the embedded space. Now the metric here has this W in front of it, which I'll talk about in a second. This is a weight associated with every dimension. And I'll talk about this in the next page. But for now, let's just assume this is actually set to 1. So now let's take a step back and think about this embedding algorithm. So let's imagine this embedding algorithm is a clever one. So it realizes that we have two-dimensional feature space. One is page, yeah, sure. Where's the small n? Also, these are different, so m different pairs of nodes that I sample. So I cluster S number of clusters in my feature space, and from the total nodes, I sample m different pairs of nodes. Yeah, so maybe I should have called a different letter here to make it a little bit more clear. Yeah. Pairs of nodes, that's correct. These clustering? So the clustering is for us to, from a scalability perspective. So for small networks, you could potentially have pairs of nodes for every single one of them. But for larger networks, you want to kind of cluster it so that you have nodes that are similar to each other grouped together, and the ones that are not similar, again, they're far apart. So we cluster the nodes, and then we sample from, for example, within the clusters and correct, exactly. So yeah, go ahead.
Because if you have a lot of clusters, if you sample uniformly, you would mostly sample not within clusters.
Yeah, so the probability that we have for sampling is proportional to the size of the cluster, so that we adjust for that. So if we have, so if the embedding algorithm is a clever one and it mimics exactly what we're doing on the right-hand side, so it sees that dimension 1 is page rank, dimension 2 is centrality, and creates exactly the same measures on the left-hand side, well, the vector here is identical to this vector on this side. In other words, these two vectors, if I look at the similarity between the two, will be very similar. On the other hand, on the other extreme, if our embedding technique is a random number generator, so we create a k-dimensional noise space, the vector that's calculated here has no similarity with the vector on the feature side. So this hints at the fact that I can measure some metric psi here that measures the similarity between a vector on the feature space and a vector on the embedded space. Now, of course, the choice of how you actually define this metric is a little bit up to you. The way we do it here is we do 1 minus the Pearson correlation squared, which means we don't care about the positive or negative correlation, but if you care about, you want to break that symmetry, you can design your metric to be slightly different. I'll talk about why we choose this in a second. It's really from a predictive perspective rather than, so again, you could choose this to be something different. So what does this actually mean? So this means that psi here will give us a measure between 0 and 1. 0 means when these two vectors are very similar to each other or actually identical to one another, and 1, which means that they're not similar to each other. So if we take a step back, this means that if I take one metric, let's imagine page rank, and I calculate this psi value and the psi is 0, it means that my embedding algorithm was able to really well represent that metric. On the other hand, if it's 1, that means my embedding algorithm was not able to represent that metric. So now we have a quantitative way of understanding what features are being represented by the embedding algorithm. It kind of gives us an insight into that. Now I want to take a second and talk about this W weight here. So now let's think about an embedding process. So we take a feature and we embed it into an embedding space. Now this feature could get embedded in any of the dimensions, k dimensions of the embedding space. So let's focus on this chart on top here. Let's imagine I have page rank, and page rank is embedded by embedding x into dimension 1. And I do the exact same metric and I embed it using embedding y, and it gets mapped, actually projected into multiple dimension. Now, of course, that's completely dependent on the embedding algorithm, but we want to be able to differentiate these two projections. So the way we do that is by saying that if I'm measuring the psi value for, let's just say, page rank, and I have these two dimension 2 and 3, again, these are just kind of a cartoon representation, have nothing to do with the representation of page rank, I can just get rid of them and they won't have any effect on my psi calculation or my metric calculation. So in other words, I can use the weights in the sort of distance measure to do a kind of dimensionality reduction. So in other words, remove any dimensions that have nothing to do with the particular metric I'm analyzing. Now this doesn't mean that dimension 2 and 3 here are useless. They could represent other features that I'm not studying at the moment, but this allows me to, again, focus the large embedding space into the dimensions that actually matter for particular analysis. So to showcase how this actually works is we kind of call this a post-optimization metric. We embed a graph using LSME, which is a structural embedding technique, and we assign random weights for an 8-dimensional embedding. Now we have no idea which dimension was PageRank mapped into, but after post-optimization, we're kind of optimizing, in other words, reducing the value of psi by adjusting this W metrics. We see that most of the weights are set to 0 because they're not really contributing anything to the representation of PageRank. There's a bit of residual here. And we can see that PageRank was actually mapped into this third dimension, or the technically third dimension of the embedding space. So this is nice because it also gives us a visibility inside the embedding space. We can see how do certain features get mapped and represented in the embedding space itself. Now the optimization, of course, has a condition so that the weights have to sum to 1, so that kind of takes care of that. And we can repeat this process for any metric that we want, any feature. So here's an example of 12 structural features that we calculate for a graph. And we can calculate psi value. Again, these are the kind of post-optimization psi value for every one of those features. And what this tells us, again, scale between 0 and 1, how well is this particular embedding technique, which is Rolex, learning those features. So for example, closeness centrality is learned a lot better than this guy over here, which I think is load centrality. So now we have a signature of how well, in this case, Rolex is learning a collection of features. Now this list here, of course, is up to us. We can calculate hundreds, maybe 200 different metrics. So that gives us, if we have a lot larger collection, we get a much better description of what the embedding space is representing. So with that in mind, what I'd like to do is to walk you through a couple of examples of how you can take this framework with these ideas and apply to both first synthetic graph and then a real network. So we start from a synthetic graph because we can control everything. Obviously, we know what the ground truth looks like. So the synthetic graph that we've designed is a large graph, a relatively large graph, composed of these structurally unique subgraphs. So we have a web star and a D star, where each one of them for the root node has a very kind of unique structural properties around the root node. And all of them are kind of combined together in this sort of random way. We have a technique to combine them together, but the goal is to make sure there are no communities being formed. And the reason is because we want to build a synthetic graph which is purely structural in properties. And so what's the goal here? The goal is to embed all the nodes in this graph using the various different embedding algorithms, for example, classical and structural, and then use those features to see if we can build a classifier to identify these root nodes from the rest of the nodes. And then one thing we also want to do is we want to analyze this graph without the labeled nodes using our framework to see if there's anything we can draw from an information perspective using our framework that could help us with downstream tasks such as classification. Okay, so here's all the results in one page. I'll start with the kind of chart on the left-hand side. So what we've done here, similar to the previous kind of graph that you saw, is the psi calculated for every one of these embedding techniques for these 12 different structural features. So let's start with the classical embedding, so node to vec and deep walk. And what we can see is that the value for this psi is very close to 1, which makes sense because we know that classical embedding techniques are there to learn proximity within a graph. So it makes sense that they're not really learning these structural features that well. So that's kind of an obvious thing, and we were hoping to see, and that's exactly what it comes out. On the other hand, if you look at these structural embedding techniques, we can see that each one of them learns these structural properties to a different degree. So for example, roll to vec is not really performing well on this particular data set. That doesn't mean roll to vec is not a good algorithm. It just means that based on just taking the parameters that comes with roll to vec out of the box, applying to this particular graph, this is what it learns. Now it could be learning other features that are not within this 12, but again, this is what we see here. On the other hand, we can see Rolex or LSME perform quite nicely. Again, struct2vec, not too bad. So I would imagine if I use the features of each one of these embeddings, so not really mixing them, but each one of them separately, to build classifiers for identifying these root nodes. Of course, these two they shouldn't perform that well, and then I would imagine roll2vec really performing the worst out of these structural embeddings. And if we go to the accuracy calculation here, we can see exactly that. So again, deep walk and node2vec not performing really well, and then roll2vec is last from a structural perspective, and then the rest is kind of shown here. And the one thing I want to point out is that the node features here is taking these kind of raw calculations or the metrics and building a classifier using that. And given the fact that our network is very structural, of course we expect node features to perform really well, and this is again what we see. So the take-home message really from this chart here is that we can use our framework to do multiple things. We can understand which one of the frameworks could potentially, or which one of the embeddings could potentially perform well, what features specifically are they learning, And of course, you can now use, for example, analysis like this to know how those features are actually being mapped into the embedded space. Now, one last point I want to point out before we walk through the real network is by looking at these charts, this allows me to see that, for example, LSME and Structivec have a very similar profile. So if I want to combine features from different embeddings, I should probably combine Rolex and one of these guys rather than these two together, because Rolex has a much broader representation of different features. So the total feature space, if I combine them together, is much richer than, for example, randomly picking embeddings. So it kind of gives me some guidance from that perspective as well. Now, of course, this is a synthetic graph, which means that everything should, hopefully work phenomenally well. But now let's take a look at a real network, which we all know is a lot more messy. So here's a network of Twitch, social media. So it's a kind of similar to YouTube. People stream games and things of that nature. Here, every node corresponds to a user. Edges would correspond to, I think, a follower-following relationship. And the labels are whether it's a mature content channel or a user or non-mature. And here, mature could mean, for example, violence or swearing on the channel or something like that. Now, the network does come with a lot of metadata, but what we kind of do in our analysis is we strip away any metadata and we only focus on the actual graph structure and information that we can extract from the graph itself. The task is, again, very similar. We want to embed all the nodes using various different embedding techniques and then use our framework to see if we can draw any conclusion, at the same time build a classifier for a binary classifier, mature versus non-mature accounts. So here, again, very similar output. The scales here are slightly different just because some of these things are pretty close to one. I just wanted to kind of zoom in and blow up just to showcase how the performance looks like. Now, one thing before we jump into these results, if we go back to the chart here, is that we can see, hopefully kind of comes clear, is that the red dots here are clumped together on top here, and the non-mature contents are kind of on the bottom. They're not clear communities, but clearly it's not a completely mixed up kind of classes of nodes together. So again, we can see DeepWalk and Notivec, the values are very close to 1. They're not really learning structural properties, which is expected, but that the behavior or kind of the profile of the structural embeddings in this particular case is very different to the synthetic one. So what first thing it tells us is that embedding algorithms could learn slightly different things depending on what network they're applied to. And that logically makes sense. Here, Structivec is now really performing well. On the other hand, Roltivec, which wasn't performing well in the previous graph, is actually learning a relatively diverse set of features, although the values are not great. And then again, the remaining are pretty self-explanatory. So if you look at the accuracy profile, the first thing I want to point out is that DeepWalk and Notivec actually perform the best. And this is kind of obvious when we look at the graph itself, where you see, again, not clear communities being formed, but there is some segregation of classes within this network. So this does translate to these two embedding techniques performing the best. And this is one of the challenges with structural embedding techniques, is that when you have a labeled data set, you can't really know whether structure is going to play a role in the classification. That's something that, again, is intrinsic to the network. And we can see here that, for example, classical embedding techniques perform decently. But if you look at the structural techniques, we can see that there is a correlation between how they perform in the classification task and the performance in our framework. So we can see Roltivec is performing the best, and then the remaining of the embeddings kind of follow behind. One thing I'll point out here is that node features perform worse than Roltivec. So what this means is that clearly the classes or the classification is not purely reliant on the structural properties. So there is something else that Roltivec is learning that's outside the scope of these features, or the fact that Roltivec does have a random walk component to it potentially could be contributing to the success of Roltivec. So that's one of the questions or challenges that we are working on right now. So really from my perspective, I think what we should be doing is to expand these features or have features that could give us some insight into what type of non-structural properties could these embeddings also learn. So again, the framework is still relatively useful, even though it's not as useful as a synthetic graph. But again, that's not really up to us. When you use a real network, you're dealing with what you have. I know I have only a few minutes left, so I'll just conclude a summary, which means that we build a structural embedding techniques that answers these two questions: what are embedding techniques learning, and how well are they learning it? We've applied this, showcase it on both synthetic graphs and also real networks. And some of the interesting things that we want to look at next is looking at how features are mapped into the embedded space, because if you have two embeddings that perform very similarly, one which is organizing the data better in the embedding space could potentially be a lot more useful as compared to one that scatters the information or representations in the embedded space. So kind of digging into that a little bit. And with that, I'd like to thank you for your time. Thank you.
Thank you very much. Oh, so we have questions.